Resultant forces, here we are again. So this video is like the fourth one now in this type of series. So if you remember on a couple of videos or the 3 videos before this, we were working out resultant forces, horizontal forces, vertical forces, the resultant of them 2 forces, and the angle of these shapes. So go back if you need to see them videos. But now we're going to take it a bit further. I've added on now some dimensions of where these forces are and where they are applying. I've also put a pivot point. All that means is it's fixed at that red point there, look, pivot point. There, let me draw it for you. Pivot point is there, look. So it's fixed about that point. Okay. So all these forces are going to make this thing spin about that pivot point. In the previous examples, we didn't have any dimensions or a fixed point. We were just working out the resultant force. So we're using this example again, and all we're going to do now is find the last bit we're going to find. Some of these words, don't worry about them. So find which way the object will spin by finding the total moment. This object now is going to spin about this pivot point here. We need to find which way it's going to go. It's either going to go clockwise or anticlockwise. But we can use moments to find that. Then I'm going to draw the line of action of the resultant force. We've drawn it up here. This line here is the line of action. But I'm going to give it a position now. And I'm also going to draw the equilibrant. That just means the equal and opposite. Equal and opposite to the resultant force. Because if you've got a resultant force that's making something spin, if you put an equal and opposite force to that resultant force, called the equilibrant, it will stop this thing from spinning. The words sound posh, but it's quite easy once you get there. Okay? So in a previous example, this example, we worked out the resultant force was 7.61 kilonewtons coming down at 67 degrees. So I'm going to draw that here somewhere, just so it reminds me of it. 67 degrees, and it was 7.61. So 7.61 kilonewtons. So the result of all of them forces is 7.61 coming down like that, 67 degrees from the horizontal. That's from the last video. So now we need to work out now where that line of action is. I've now given us a pivot point and some direction, so we need to work out the first one, which way is this thing going to spin? It's either going to spin that way, clockwise, or it's going to spin that way, anti-clockwise. I'm going to call clockwise. If it's spinning clockwise, I'm going to give it a plus. If it's going the other way, anti-clockwise, I'm going to give it a negative. So we're going to work out now which way this thing is spinning. Is it spinning clockwise about that pivot point, or is it spinning anti-clockwise about that pivot point? And all I'm going to do is use moments. We've done them before. So a moment, magic moments. A moment, which is like a torque, a turning moment, is force times distance to the pivot. Distance. So all we're going to do, we're going to find the force in newtons, and we're going to multiply it by a distance in meters. So the unit of a moment is Newton meters. Same as a torque, and all it is this. If that's my force, that's my pivot point, I'm doing force times that distance. It's always 90 degrees. So I'm just doing force times distance. If it's going clockwise, I'm going to call it a plus. If it's anti-clockwise, negative. And I'm going to add them up to find the total. First one. Let's go number 10. Okay, different color. Come on. So here's my number 10. So there's my force. So here's my number 10. So I'm going to do force times distance. There's my force, there's my distance, which is 0.3. Force, 90 degrees, the distance. So I'm going to do force times distance. So my force was 10 times by 0.3. Okay, force 10, look, distance to the pivot point was 0.3 in by there, which gives me 3. It's kilonewtons, so it's going to be kilonewton meters, because a force is in newtons, meters, look. We're just in thousands here, so 3 kilonewton meters. That force is going to make this thing spin about that point clockwise, because it's going to go that way in it. Put a clockwise by there. Leave it plus. Next one. 5. There's my 5. Look, that's the force. The distance here down is 0.25. It's going to be 5 times by 0.25. It's going to be going anti-clockwise, so I'm going to put a minus in front of it, because I've called anti-clockwise minus. So I'm going to go 5 is the force times by the distance to the pivot point, which was 0.25. 0.25, which gives me a number 1.25 kilonewtons per meter. It's going anti-clockwise, so I'm going to put a minus in front of it there. Anti-clockwise, so I put a minus. It's going the other way, isn't it? That 5 is going to make this thing spin that way about that red dot. Lovely. This number 3, we can ignore it really, because it's in line with the pivot, so it's not going to make it spin. Just going to pull it off the hinge. If you open a door on a hinge, it's not going to spin as it just pulls it off the hinge. So this one is going to pull this thing up. It's not going to make it spin because there's no distance, so it's naught really. If you want to put it in, you can. You can go 3 times by naught, which gives you naught. There's no distance away from the pivot point. So you can ignore it if you want to, because that 3 is just going up like that. There's no distance away from this. It's in line with it. So we can ignore it for now, as far as moments are concerned. The last one is this 2. So this 2 now is there. Look, there's my force. 90 degrees is down there. Look, it's not a very good color, that is it? 90 degrees there. Look, force times by 0.5. 90 degrees. There's my force. There's my line of action. Sorry, line, distance to pivot. So it's 2 times by 0.5. Let me get my pen back. It's going to be 2 times by 0.5. Gives us 1 kilonewtons per meter. Right? And it's going to make it spin clockwise. That thing would go clockwise about that red dot. So it's clockwise. So put clockwise there. Leave it as a plus. Total moment, just add them up. Total mom ent. Just add them up now. 3 plus minus 1.25 plus 0 plus 1. So if you add them all up, don't forget the minus, you get a total of 2.75 kilonewtons per meter. It's plus, which means going clockwise. So after all of that, these forces now are trying to make this thing spin clockwise about that point. So we've done, find which way the object will spin. We've done that, tick. We've done that. Now we've got to draw the line of action of the resultant force. Well, here's my resultant force. There, look, 7.61. Okay, 7.61. We know it's coming down. And we now know it's 67 degrees. And we now know it's going to spin it clockwise. So the line of action of the resultant force, I'll quickly draw it again. Because now we've got to draw this line of action. There's my pivot point there, look. And we know, let me get my pen, we know it's coming down like that, look, 7.61, 67 degrees, and it's spinning it clockwise. So it's either going to be like that or like that, either side in it. But we know it's spinning clockwise because we worked it out, which means it's got to be this one here, isn't it? Because this way will make it spin clockwise. This way would make it spin anti-clockwise. So it's got to be this side of the pivot. So you want to draw now with a ruler. That's my resultant force. Resultant force, line of action. We know it's coming down like that because it's got to be 2.75 clockwise. Got to spin it clockwise. It's going to be 7.61 at 67 degrees. So this is going to be 7.61 kilonewtons. The angle in here is 67 degrees from the horizontal. We now need to find how far away we are from there, which we can do. I'm going to leave that D, the distance from there, look. We know that moment is force times distance. And it's that D we want to find. We know the moment because we just worked it out. And we know the force because it's 7.61. The moment is 2.75. So to find D, I'm going to go moment divided by force gives me distance. The moment was 2.75, and the force was 7.61. They've both got kilo behind them, so they cancel out, so I put it in. That gives me 0.361 of a meter. All that means is perpendicular distance away, this line of action, 0.361 meters away. So you want to label that as well. So we now know the line of action, the resultant force line of action. It's coming down like that at 67 degrees, 7.61. It's 0.361 of a meter away. It's going that way because it's going clockwise. So we've drawn the line of action there, look. Now we've got to find or draw the equilibrium. That just means equal and opposite. Equal and opposite. I don't want my pen. Equal and opposite. Because it's spinning and we don't want it to spin. So all the equilibrium is a line. It's a force that you would apply in a different direction, equal and opposite direction like that. You use a ruler. So this is my equal and opposite. So label if you want to. Equal and opposite. Something wrong there, look. Equal and opposite. So that force there, that purple one is going the other way to this red one. The resultant force is trying to make this thing spin that way. But we don't want it to spin. We want it to be static because we're doing statics, as in not moving. So to stop this from spinning, you've got to put an equal and opposite force. The other way is just draw a line like that. You haven't got a scale, draw it. And that will stop it spinning and make it static. Line of action, resultant force, and equal and opposite to the resultant force.